All right, let's begin. So hey everyone, hope everyone had a good weekend. So last week we talked about generative models. I hope everyone enjoyed my lecture last Thursday. And this week we're going to go into two more lectures, both on reinforcement learning. So today I'm going to kind of set up the basics of reinforcement learning, go through some of the basic algorithms. And on Thursday, we're going to go a bit more in depth into reinforcement learning and also look at how reinforcement learning methods can help us in these multimodal problems like text generation, like we talked about last Thursday. So anytime, feel free to just type on the chat if you have any questions. So today's lecture, I'm going to give a very brief and high-level introduction to reinforcement learning. And most of this content is taken from some of these amazing courses at Berkeley and CMU. So if you really want to go in depth into the reinforcement learning and look at more applications, look at more of the theoretical insights, definitely do check out these semester-long courses. I'm going to try to distill the most useful information and also most of the applications to language and multimodal into these two lectures. So let's begin. So the main things that we're trying to cover today are first the introduction to reinforcement learning, setting up the problems, especially using this framework called Markov decision processes. It's a theoretical framework that allows us to reason about the objectives and the algorithms for reinforcement learning. We're going to look at some simple cases of MDPs, and if everything is known, that means that it's easy to solve, it's small in scale. We can actually solve these MDPs exactly using algorithms called value and policy iteration that I'll go into. However, in the real world, where a lot of things are unknown and a lot of things are really high dimensional, you can't solve these MDPs exactly. So we're also going to give a brief introduction to how we can use function approximation and neural networks to solve these unknown MDPs. So let's begin. So I'm pretty sure everyone's heard of reinforcement learning. It's this new research area that has particularly gained a lot of interest recently because of the combination of reinforcement learning and deep neural networks. So in this new area called deep reinforcement learning. And it has seen many, many successful applications in the real world, including self-driving cars. They use some aspect of reinforcement learning. Recently, they've been able to train these AI methods to beat humans at Go, a game that was long thought too difficult for humans to play, again using reinforcement learning methods. They've been also shown to do really well on these Atari games, which require a lot of human dexterity, but AI agents can also be trained to get better than human performance. And likewise, we've also seen a lot of applications of RL in the real world towards building robotics for manufacturing, playing multiplayer games like FIFA, and also building robots that can effectively navigate in the real world and interact with humans. So what exactly is reinforcement learning? So some of you might have seen this diagram before. Here's a very general setup that everyone uses to introduce reinforcement learning. Essentially, there's two key components. You have an agent that is placed in an environment. And this agent is going to start from a particular state in the environment known as S0. That's your starting state. You can think of these states as parameters of the environment that defines where the agent currently is. So in my case, I'm currently at this particular spot. That is where my starting state is. And whenever the agent is at a state, it's going to take some action. And this action is chosen from a set of all possible actions that I can take to interact with the environment. So very simple cases are, going left, going right, sitting down, or standing up. These are actions that I can take. And whenever it takes an action, the environment is going to, in response, spit out two things. The first thing is a reward, R0. So a reward tells the agent how well it's currently doing in its environment, whether positive or negative, and at what magnitude. And the environment is also going to tell the agent what's the next state that it ended up into. So if I move left, maybe I don't observe any reward, and I move one particular set to my space to my left, that will be my new state. So this sequence of interactions from states, actions, observing rewards, and going to next states defines a trajectory of the agent interacting in this environment. And this trajectory goes on until whenever the agent stops interacting with the environment. So clearly, this is a very general setup. And let's just look at it in the context of one of its examples here. So let's just say FIFA, for example, because I love playing FIFA. So initially, you're going to start at S0 at kickoff. So you have all 11 players on each side, each in their particular positions. Those are the initial states. And what are actions? The actions will be, each of these 22 players either moving around, up, down, left, right, or, kicking the ball or passing to another teammate. So these are the possible actions that you might have. And what are the rewards then? So the rewards could be, positive reward if you manage to score a goal, or if you manage to successfully pass the ball to your teammate, or if you're able to successfully prevent the opponent from scoring against you. So here are examples of positive rewards. And maybe you'll get a negative reward if you commit a foul, or if you fail to complete a pass, or if the opponent scores a goal against you. So again, this framework is very general. It almost encapsulates any form of interaction between single agents, multiple agents in their environment, and observing some reward. So let's go a bit more in depth. So a Markov decision process is basically a way to formalize many of the terms that we just talked about. So Markov decision process consists of 7 terms. It consists of a set of states that the agent could be in. It consists of a set of actions that the agent could take. So whenever the agent samples an action, it must fall under one of the set of states. It defines a transition function. So if you're in state S and take action A, it tells you the distribution of next states S prime that you will end up in the environment. Most of the times, these transition functions can be deterministic. So if I move up, down, left, right, I will deterministically end up in the next state. But at certain times, it might also be stochastic and random. It's a reward function that is also given by the environment. So it tells you if you're in state S and take an action A, ending up in state S prime, what is the reward that I observe? You're going to see a start state. And I'm going to go into a lot more detail in discount factor in the 2 slides. So let's pause on that for a bit. And you're also going to have a horizon H, which tells you a total length of interactions between your agent and the environment from which you obtain these trajectories. So one important thing of these Markov decision processes, as given by the name, is that it must follow this Markov property. And this Markov is the same term that you've seen for hidden Markov models, Markov random fields. It essentially says that all the information I need to reason about my next states and my next actions should only be contained in the previous state and action. It should not depend on states before that. In other words, we should be able to throw away all the history once this current state is known. So just to give an example, so let's just say I am upstairs in my room, and my roommate tells me to go downstairs and get him an apple. So that is one natural language instruction that is given to me as state S0. So S0 might be my current position upstairs in my room, and this natural language description that my roommate wants me to go get an apple. So there's 2 possibilities of defining a Markov decision process as I go and get this apple. One thing is that as I'm going to go from my room upstairs down into the kitchen, I'm going to take all sequences of states that I'm currently observing, and I can define these states using 2 choices. The first choice is just to keep my position in the house. The second option is to keep my position in the house, and I always append this natural language instruction behind it, that I should go to the kitchen and get an apple. So you think about it, one of these actually satisfies the Markov property and one doesn't. So the one that satisfies the Markov property is the one where each state consists of my current position in the house, as well as the natural language description together with it. So in other words, what ST would be one step away from the kitchen, my current state, as well as the description that I should get an apple. That satisfies the Markov property because now I can throw away all my previous information, all the previous instructions and my previous states, and just condition on ST and AT. So on the other hand, if I just keep the natural language instruction at S0 and subsequently only contain my position in the house, then by the time I get to ST, I need to condition on S0 to be able to realize that I'm supposed to pick up an apple. Just a very simple example to show how we can actually turn something that maybe does not consist of the Markov property to something that respects the Markov property by propagating this information towards the later states. So this is quite important. A lot of, if you look at all these applications like natural language navigation and all, they're given these actions and you're supposed to follow these instructions. They just give it at a start, right? So technically they don't respect the Markov property, and they're not technically Markov decision processes, but it's something to keep in mind as you design these algorithms. So then what is the goal in reinforcement learning? So you've seen that you have an agent taking states, you have an agent taking actions and going to different states and an environment. The goal is usually to maximize your total discounted reward. So as you start taking states and observing rewards, I want to sum up all the rewards that I'm going to observe throughout my entire sequence of interactions with the environment. So that will be RT plus 1. So the reward at GT at a particular time step T will be the reward that you obtain in the next time step, plus subsequent rewards that you obtain at T plus 2, T plus 3, and so on. And notice that we're multiplying by a gamma factor here, gamma the first time and gamma square the second time and gamma to the power of 3 to the power of 4 subsequently. So this gamma is actually what we saw previously as the discount factor. So why do we need a discount factor? So there's a couple of reasons. One reason is that you can draw an analogy to economics, which states that money that I have now at this particular time step is more valuable than money that I am promised to get in the future. So I should discount whatever rewards I get in the future. In both theory and in practice, having a discount factor also helps us to reason about convergence, because it encourages our agents to get to the final goal faster instead of just sitting around and collecting rewards. So it's also useful in both theory and in practice. And if you look at what values gamma can take, gamma has to be between 0 and 1. Gamma close to 0, or even when gamma is exactly 0, you're basically foregoing all positive rewards in the future, and you're just trying to maximize your immediate reward. That would be myopic evaluation. And if gamma is close to 1, then what you're trying to say is that I care a lot about rewards in the future, and might prefer really large rewards in the future and forego short-term rewards in the near future. So different settings of discount factor also allow us to design different sets of algorithms depending on whether you want to care more about immediate reward or long-term reward. So I have a question, someone asking a question. How do we condition on the initial state to maintain relevance of subsequent actions to the goal? So I think you're talking about this Markov property here. So you just use the same example that I did, which is both states being the position in the house and the instruction that you're given. You can always just define your states as appending this particular natural language instruction up until you find it to be useful. So you always append it, then that would respect the Markov property. In practice, you can also use things like LSTMs and kind of assume that LSTMs have memory, so it's always capturing this information into future states. Hopefully that answered this question. Yep. So now we've seen what MVP is. We've looked at states, actions. We looked at the goal of maximizing this cumulative reward. So what do we actually want to do in reinforcement learning? So we actually want to define a policy in order to maximize this cumulative long-term rewards. So what is a policy? A policy is basically a distribution at a particular state over actions that you can take at that particular state. So having this policy will fully define the behavior of an agent. So a policy is basically like a map like this. So at every state, it tells you the action which you should take. So maybe here I want to go upwards and rightwards towards the diamond because that gives you the reward. And if I'm in a state like this, I don't want to go upwards because I'm observing really negative rewards. So policy fully defines the behavior of an agent. And our goal in reinforcement learning is to find out this policy that can actually maximize our long-term cumulative rewards. The policy is stationary. That means once you've trained the policy, it just stays fixed. You don't change it anymore. And it's during learning where you want to start with a random policy and collect experience in the environment to actually obtain a good policy. Most of the times, your policies are random. We'll see why we need that in a second. But as a special case, you can also reason about deterministic policies in very similar ways. So just to summarize, we've looked at MVPs. We've seen how an agent with taking actions and going into different states and an environment and observing rewards is a very general framework that encapsulates many of the real-world reasoning tasks. We've seen that the goal of the agent is to maximize his cumulative reward multiplied by a discount factor. And you want to learn the best policy, argmax over all possible policies, that best maximizes your cumulative reward. And each of these policies will define a particular distribution over actions that the agent should take from different states. So here's the main goal of reinforcement learning. So just to summarize some differences between reinforcement learning and supervised learning. In RL, we usually care about taking decisions over multiple time steps and observing cumulative rewards. While in supervised learning, we usually make a one time step decision and we're done. And because we're doing sequential decisions over multiple time steps, you want to maximize cumulative reward, sometimes foregoing immediate rewards and really looking at your long-term rewards that you might get in the future But for supervised learning, you don't really care about future rewards. There's just a single immediate reward that you would like to optimize. In RL, you also might have this problem of sparse rewards. So again, if you're playing this FIFA game, if you're defining these rewards as having scored a goal, you're not going to observe that many rewards as you play this game between two teams. So that's a sparse reward problem. In supervised learning, you usually have very dense supervision. You have labels immediately. So you never really run into this sparse reward problem. And in RL, we've seen these MDPs, but these MDPs might also be unknown. So you might not know the full extent of all the states there are. You might not know all the actions there are, and you might not know certain rewards. So there's also a degree of uncertainty in the environment in RL, but you don't usually have that in supervised learning. But before going into RL, there's actually a very close analogy to supervised learning, which is called imitation learning, that I want to go through in just one slide. So what is imitation learning? So again, let's say you're in this agent in an environment. Let's say you want to train a self-driving car. What you can do is that instead of getting the car to start randomly, and that's going to be obviously dangerous, what you can do is you get a human driver to sit in the car and just drive it as a human driver would. And you can collect these video demonstrations of how the human driver drives the car. So human driver will start in state S. Maybe you're in your runway. You will pull out. You will turn left, and you would follow the road signs and eventually reach your destination. And we know that these are very good trajectories because human experts are driving them. So these are called expert trajectories. And once I have such an expert trajectory, I can basically decompose it into a supervised learning problem. So at every state S, as observed in this set of expert trajectories, just try to build a data set that maps S0 to your best possible action A star 0 as given by the human expert. And these expert trajectories therefore give you a really large data set that predicts your expert action. And you can actually train a self-driving car using supervised learning to predict this expert action, right? By taking in maybe the image and building a neural network that predicts this set of actions as given by the human expert. And this actually performs reasonably well. This is a big class of research and reinforcement learning called imitation learning that leverages a lot of human demonstrations and human experts. But there's some issues. One issue is a distribution mismatch between training and testing. So let's say if I only collect expert trajectories of humans driving in the summer, they're not going to be able to train a model that drives in winter. It's also hard to recover from suboptimal states. So in this set of expert trajectories, all these states are perfect. It always stays on a road. It always follows the road signs because an expert are labeling these trajectories. But what if for some reason you make an incorrect action? Even if you do supervised learning, it's going to be imperfect. So what if you make an incorrect action and you end up on the curb? Then you're not going to get any information from these expert trajectories how to recover from the curb back onto the road. So it's not going to be able to recover from these suboptimal states. And also, sometimes it's not safe or possible to collect expert trajectories, especially if you want to train, like nowadays we have robots that go onto Mars or robots that explore volcanoes. You can't really train humans to design the paths for these robots because it's not safe to go into a volcano. But this is the closest intersection between reinforcement learning and supervised learning. And this class of algorithms, taking some information from human experts, kind of doing some supervised learning, but at the same time doing some reinforcement learning using algorithms that we'll see in a bit, they actually tend to perform the best for these safety critical real world applications. But yes, now let's go into the reinforcement learning aspect. So here are I'm going to first start by defining some important definitions in reinforcement learning. So these are called your state and action value functions. So starting with a state value function. So a state value function, we denote it as a V of S with a superscript pi because these state value functions depend on what your current policy is. So what this V of pi of S basically means is that the expected return starting from state S and following your policy pi. So in other words, you're going to initialize your state ST to be S, starting from this state S, and you're going to compute G of T, which you call is the cumulative long-term discounted reward. And then you're going to take an expectation over pi over all the randomness in a data set because your policies might be random and your transitions might be random as we've seen from MDPs. So essentially this function tells us that if I give it a state and I keep following my policy pi from this state, what are the long-term expected rewards that I'm going to observe? And likewise, I can define it for action value functions. So instead of defining it for a state, I'm going to input both state and action. In other words, if I'm at this state and I start taking this action and I continue following my policy pi, what is the expected long-term reward that I'm going to observe? So very simply, this tells you how good your state or your state action pairs are under your current policy pi. And likewise, I can define my optimal state value functions and my optimal action value functions. Very simply, we saw that the previous state value functions and action value functions depend on a particular policy. If I take max over all possible policies, then I'm getting, if I take max over all possible policies, then I can obtain the optimal state value function. So that means if I start from state S and I act optimally using the best policy, what is the expected long-term reward? And likewise, if I'm at state S and taking action A and following an optimal policy subsequently, what is the expected long-term reward that I'm going to observe? So the goal of reinforcement learning is really to find these optimal state value functions and optimal action value functions. So what it means to solve an MDP is that, given an MDP and a particular policy, I want to find the state and action value functions. So I want to be able to compute these two things for a given policy. And that's a prediction problem. And for the optimal control problem, it's very similarly related. It basically involves another maximization over all possible policies. So this will involve finding the optimal policy that achieves your optimal value function and your optimal action value function. Just to summarize, so these value functions would measure how good a particular state or state action pair is for a given policy, and these optimal value functions will measure the best possible states or actions under all possible policies. So for state values, you have V pi and V star, and likewise for action values, you have your Q pi's and Q stars. So all these four terms are related to each other, your state value functions and your action value functions. We've seen that if you have a state value function for a particular policy, you can maximize over all policies to get the optimal one. And likewise, you can do the same for your action value functions. And what you can also do is you can interchange between your V stars and your V's and your Q's. So to go from your Q stars, I can take the best action, and that will give you my V stars. And if I have a QSA for a particular policy pi, I can take an expectation over this policy. So that would sum over all possible actions weighted by the probability of taking that action to get my state value functions for that policy. So all these are interchangeable. So again, why did I say that the whole goal of reinforcement learning is to find these Q stars and V stars? And that's because if you have a Q star, you can actually define, you can obtain the optimal policy. So I can take the optimal policy by simply finding the action that leads to an argmax over my Q star SNA. And that measures, the long-term cumulative reward under the best possible policy. So if this action achieves this best long-term cumulative reward under the optimal policy, then that is the best action that I can take at this particular state. So you would take that action with probability 1 and 0 else. And you can also obtain the optimal policy with your V stars. So how would you obtain it with V stars? You actually have to do one step look ahead. So what that means is that, let's say you're in a particular state S, and as a policy, I want to evaluate how good each of my actions are. So for each action, I'm going to take it. And by taking this action, you're going to transition into a particular next state. And for each of the next states that you transition to, you're going to observe a reward. That reward from state S, taking action A and going to the next state. And once you go into this particular next state S prime, you can actually add up the discounted optimal value of state S prime under the optimal policy. So that's your V star of S prime. And together, these, under the expectation rule of all possible states S prime, because there's randomness in your transitions, this whole term will define how good your particular action is. And you want to take the action A that maximizes this term. Right? This essentially is a one-step look ahead. So if you're in state S, just having V star of S isn't really useful because you can't reason about any actions. But if you add v star of your subsequent states S prime, then you can reason about how each of these actions are, both in terms of your immediate reward and also your discounted future optimal rewards given by your v star of S prime. And just writing out these expectations, the expectation over S prime is basically averaging over S prime as given by your transition probabilities. So therefore, the summary here is that if you have your Q stars and your V stars, you can actually obtain your best possible policy, your pi stars. And therefore, the whole goal of reinforcement learning is to find these two values, your Q stars and your V stars, given interactions between your agent and the environment. So then the question is, how can we find these? So I'm going to start by going through three methods. Each of these three methods have different assumptions and different trade-offs. So the first method is called value and policy iteration. So what I'm going to do is that I'm going to look at GT. Again, GT is this object of interest, right? This is your immediate rewards times your discounted rewards into the future. I'm going to factor out gamma. And once I factor out gamma, I can basically rewrite this recursively as your GTs in the future. So what this value, the value of a particular state under a policy, what that basically is that the expectation over GT under your policy pi. So I can use my GT expanded into my immediate reward times gamma future rewards. And my expectation of the future rewards under pi is basically V pi of ST plus 1. So what this term is I'm going to expand it out. The expectation under pi is basically summing over actions, each action weighted by the probability of taking that action. There's also an expectation over S prime, because each of these rewards, each of these state and action that you take might lead to a different set of different next states. So this expectation over S prime is basically a summation over next possible states, your state transition from SA to your next state S prime. You're going to observe an immediate reward, and you're going to add a discounted value of the future states under your policy pi. So now I've been able to recursively write my value functions for a particular state S with respect to the value functions of future states S prime. And this equation is one of the most important equations in reinforcement learning. These are called your Bellman expectation equations. So just to make that more clear, we can also kind of derive it by picture. So it's very, very helpful to draw all these trees out, where these white circles are your states and these black circles are your actions. So for each state, you're going to label your value function for that state, and you're going to have your value functions for subsequent states. And our goal is to really look at how the value function of state S interacts with your value functions of state S prime in the future. So how do you relate these two? Well, first of all, you know that at this state S, you might take many possible actions, right? In this case, there's two possible actions you can take. So I'm going to take an average over these two actions as given by my policy, right? My policy might say this action is 0.9, this action is 0.1. I'm just going to weight these two actions according to what the policy says. Once you've taken an average over your actions, let's say you went to here, this action, and then you have to take an expectation over your next states S prime. Because whenever you're in a state taking an action, you might transition into multiple next states just because of the randomness in the environment. So I'm going to take an expectation over my next states S prime. That's this red thing here. So that'll be summing over S prime multiplied by each of the transition probabilities to each of these S prime. P of S prime given S and A. And for each of these, you're going to observe an immediate reward that follows from going to this particular state S prime. And you're also going to observe a discounted value function of your next states. So that will be gamma V pi of S prime. So this is like a proof by these diagrams of how your V pi of S, your value functions for S, relates to your value functions for your next states S prime. And likewise, I can do it for my Qs. It's very similar. So now I'm starting from a particular action. Taking this action will allow me to go into multiple next states. So I'll take an expectation over these next states. For each of these, I observe and reward. And once I go into next states, there's also a set of possible next actions I can take. And that is given by an expectation over my policies over next actions A prime from this next state S prime. And for each of these actions that I take, I'm going to multiply it by the action value function at this next state and next action. I'm going to discount it for future rewards. So again, this is how you relate your action value functions for a particular state action with your action value functions for your next states and your next possible actions. So why is this useful? So again, we have this one. We have this Bellman expectation equations that we just derived. In this case, I'm using the one for state value functions. What this is here is actually a linear system. So for all states S, there's this V pi, which is the object of interest, and everything else here is basically a linear transformation because your probabilities of state transitions are constants, your rewards are constants once you observe them, and for a given policy, this is also constant. So for a given policy pi, this is a linear system with your variables V of pi s for all s. And if it's a linear system with some variables and constants, what that means is that you can actually solve this exactly. So if you know all these constants and you know, and all these summations can be computed exactly, then you can actually solve exactly for your optimal, your state value functions, your V pi's for all states. And there's many different ways of solving it. One way of solving it is to solve it iteratively. So if this term appears on both the left-hand side and right-hand side, what I'm going to do is that I'm going to initialize it to some value. I'm going to set it to be the left-hand side, to be the right-hand side. I'm going to compute it k plus 1 for the left-hand side. And I'm going to set this iteration back on the right-hand side. And then I'm going to compute k plus 2 on the left-hand side. It's an iterative method of solving these linear systems of equations. But the key here is that if all of these state transitions and your rewards and these summations are all tractable, then you can actually solve these state value functions exactly. And that is exactly our first algorithm. So the first algorithm would try to estimate these state value functions using this iterative method. So at iteration k, I'm going to set my state value estimates on the right-hand side and try to compute a k plus 1th iterate on the left-hand side. I'm going to iterate until I converge to the true values where both the left and right sides are equal. And this gives me my optimal state value functions for a given policy pi. So that gives me these values for a given policy pi. And then I'm also trying to improve my policy because my policy initially is also like a random policy, right? So for random policy, I'm going to iterate such that left and right hand sides are equal to get my optimal state values for a random policy. But my goal is to also improve my policy. So I'm going to take my policy at time k, and I'm going to try to obtain a better policy at time k plus 1. And I'm going to obtain this better policy by exactly using the estimates of my state value functions at time k. So recall this equation was how we went from given these, your state values, to actually your best policies using a one-step look ahead. Basically an argmax over actions, and with each action evaluated based on how good it is under your value functions. So this is an iterative algorithm. Your three variables here are again your policies, which are iterating k up to k plus 1. And for each set of policies pi, you're also going to compute your state value functions. And these two steps are known as policy evaluation. So evaluating how good a policy is. So given your pi's, evaluate your v's. And policy improvement. So given a good estimate of your v's at time k, try to obtain a better policy, pi k plus 1. And you're going to repeat these two steps until you converge. And at least in this case, where all of these are observable, your transitions and all, and the summations, or you can do them exactly, this is actually guaranteed to converge to your optimal policy. And this algorithm is known as policy iteration. And likewise, we can also do this instead of. So the problem here is that now we have to have two variables of interest. One of them being pi. So you have to both estimate pi and then go from pi to your v of pi. What you can also do is directly operate under your optimal state value functions. So instead of doing it for a particular value of pi, just straight away compute the optimal value. So that also involves us having to write our v star with respect to your v star of s with respect to your v star s prime. So for the Bellman expectation, what we saw previously, we actually summed over the leaves, right? We summed over this by taking an expectation with respect to a policy pi. But now we don't care about a particular policy. We care only about the best possible action. So instead of taking an expectation, you take a max. So your V star of S is equals to taking the best action, each of your Q stars. And you can write your Q star as an expectation over your S prime, your rewards, times your optimal state value function at the next state, given some discount. So what that basically means that you can first take a max over your action, and once you get to this part, you're going to take an expectation over different states that you can end up in, multiplied by the reward and a discounted value times your optimal state value functions for the next state. So again, this is how we can write my optimal state value function for state S with respect to my optimal state value function for state S prime. And likewise, you can also do it for Qs. I'm not going to go into in depth, but it's exactly the same thing. Whenever you have different possible next states to go to, you take an expectation, you add your rewards, and whenever you have a next set of actions to go to, you're choosing the best one. So instead of calling these Bellman expectation equations, because that was taking an expectation over your policies, over your actions, now these are Bellman optimality equations, because now you're directly just optimizing and looking for the best action A. And again, we have two values of interest. We have your V stars of S and V stars of S prime on the left and right. We can again solve this by iterative methods, by initializing V star to be some number, some initial state, initial set of values. And then I'm going to put these values on the right-hand side, and I'm going to compute an update on the left-hand side. And I'm going to do this iteratively by taking something on the right-hand side, updating it to obtain the next value of the iterate on the left-hand side. I'm going to take this value K plus 1, put it back on the right-hand side, and try to get another update on the left-hand side for K plus 2. And that is exactly the next algorithm, which is very similar to policy iteration. These are called value iteration. So instead of working with policies by estimating the policy first before converting the policies into the optimal one, I'm going to directly try to optimize for the best possible optimal state value function. So this was the inequality. This was the equality that we had. We know that they should be equal. The left-hand side and the right-hand side should be equal given by the Bellman optimality equations. And if they're not equal, we're just going to repeat this iterative process so that they are equal at optimality. And once you have this optimal state value function, I can just use a single computation to get the best possible policy. That's your pi star. So again, I'm going to repeat this until my policy converges. And if your state transitions and your rewards and your summations are all tractable, then you are guaranteed to converge to the optimal policy. Right. So again, you can do this likewise. Instead of doing your Bellman updates for your V stars, you can do it for Q stars. You get a different set of algorithms called Q value iteration. It's the same. It's just your preference whether you want to parameterize it using your V star of S or Q star of S and A. And that essentially gives us a summary of these exact methods. So what we've seen so far is that we've defined an MDP. We looked at the states, the transitions, the rewards, and we've derived two important set of equations. One is the Bellman optimality equations based on Q star and V star. Another set of Bellman expectation equations based on Q of pi and V of pi. The main difference here is that for Bellman expectation equations, you're given a policy pi, and you're evaluating the long-term expected rewards under this policy pi from a state or action. On the other hand, for Bellman optimality equations, you don't really care about a policy. You've already taken a max over all possible policies. So just given a state, you're computing the best possible long-term rewards under the optimal policy. So these values of interest, we've derived the inequalities for them based on these Bellman optimality or Bellman expectation equations.